right now, there is this mathematical, completely invisible wall passing right through the physical room you're sitting in.
Yeah, it's pretty wild to think about.
It really is,
Yeah.
because it is actively slicing the internet into these highly specific, segregated chunks. So your smartphone's web traffic doesn't unexpectedly collide with, like, your smart fridge.
Right. Or even worse, your neighbor's devices.
Exactly. I mean, we just click the little Wi-Fi icon, the bars light up, and suddenly we have the entire sum of human knowledge right at our fingertips. But behind that tiny icon is this just massive scaffolding of rules and boundary.
Oh, absolutely. And some incredibly clever mathematics keeping the whole digital ecosystem from just, well, collapsing.
Which is exactly why you're here. Welcome to the Deep Dive. We are so thrilled you're joining us today for this one.
It is genuinely one of the most underappreciated miracles of modern engineering, I think.
Yeah.
We expect our data to find its way across the globe in, milliseconds.
Right, without even a second thought.
Yeah. But the hidden architecture required to route that data without fail is astoundingly complex.
And for you, the curious learner listening right now, our mission today is to demystify exactly how that architecture actually functions. We're pulling our insights from a really comprehensive source today.
Yes, it's a slide deck from a CCNA networking course.
Module 11, specifically from Sewella Technical Community College. Our goal is to basically decode IPv4 addressing, figure out why networks constantly need to be sliced up and segmented,
And look at the mathematical gymnastics network administrators use to prevent the internet from literally running out of space.
because that threat of running out of space is a very real historical reality, right?
Oh, very real. I mean, the internet was not originally built for billions of smartphones and smart devices, so the solutions engineers developed to stretch our existing address space are just brilliant workarounds.
Okay, let's unpack this starting with the absolute foundational element, the IP address itself.
Right. Because every single device connected to a network needs an identity. An IPv4 address is, at its core, a 32-bit hierarchical address.
You've probably seen one on your computer, actually. Something that looks like 192.168.0.0.
Yeah, we call that the dotted decimal format, just because it's easier for human eyes to read.
Right, humans aren't great at reading raw binary.
Exactly. But underneath that familiar format, at the microchip level, the computer just sees a continuous string of 32 ones and zeros. And the most crucial thing to understand here is that those 32 bits are always split into two completely distinct parts.
The network portion and the host portion.
You got it.
I actually like to visualize this using like a physical home address analogy. So an IP address is essentially your home address. But just looking at a string of numbers and letters, a mail carrier might not know which part is the street name and which part is the specific house number.
That's a really good way to look at it.
Yeah. In networking, the street name is your network portion and the house number is your host portion. But just staring at 32 ones and zeros, a computer can't inherently tell where the street name ends and the house number begins.
And that is the exact purpose of the subnet mask. It acts as a secret decoder ring for the device.
A decoder ring. Okay, I love that.
Yeah, it's basically a second set of 32 ones and zeros that sits right alongside the IP address. If two devices have the exact same street name, meaning the same network bits, they're on the same local network.
Meaning they can talk directly to each other.
Exactly. But if those network bits are different, they're on different streets, and they must hand their message over to a router to carry it across town.
So to make this easier for humans to read and write out, network admins use something called prefix length, or slash notation, right?
Yes, slash notation is everywhere in networking.
Because instead of writing out a bulky subnet mask like 255.255.255.0 every single time, they simply write /24 at the end of the IP address.
Which just means the first 24 bits of the subnet mask are ones. It is a very convenient shorthand.
But a silicon processor does not use human shorthand.
No, it does not. It performs actual microscopic math. The source provides a fantastic cheat sheet here, actually.
Oh, right, the 8 values.
Yeah, noting that because subnet masks use a strict progression of borrowing binary bits from left to right, you will only ever see 8 possible mathematical values in a subnet mask octet.
And those are 128, 192, 224, 240, 248, 252, 254, 255.
Exactly. And to instantly find its network address, the device performs a process at the microchip level called a logical AND operation.
A logical AND. Okay, let's break down how that actually works because it sounds somewhat abstract.
It sounds abstract, but it's fundamental digital logic. It's happening millions of times a second inside your phone right now.
Wow, okay.
Imagine a physical microscopic gate inside the processor. The device lines up its own IP address and its subnet mask in binary, one on top of the
Okay,
other.
I'm picturing that.
And it compares them vertically, bit by bit. The rule of the gate is absolute. A 1 AND, a 1 equals a 1.
Okay.
Any other combination equals a 0. So 1 and on is 0, and 1 is 0, 0.0, and 0 is 0.
That means wherever the subnet mask has a solid block of ones, the device's IP address bits just drop straight through the gate unchanged.
Exact.
But the moment the subnet mask switches to zeros, everything drops through as a 0. It essentially strips away all the specific house number bits, leaving only the pure street name.
And in a fraction of a millisecond, the device knows exactly where it lives.
That's so cool. Okay, so the logical AND operation gives a device its exact network boundaries. But knowing your boundaries also means knowing when you are crossing them.
Right, which brings us to how devices actually talk.
Yeah, how does a device take that info and send a message to a specific machine across the room versus, a group of machines across the building?
It comes down to traffic rules. Devices generally have 3 distinct ways of communicating on a network. The most common is Unicast. Right, that is strictly one-to-one communication. One sender addressing a message to one specific destination IP address.
Sort of similar to picking up the phone and calling a friend directly.
Exactly like that. Then you have broadcast, which is one-to-all. You send one message, and every single device on that local network receives and processes it.
Sounds noisy.
It can be. The destination address for a broadcast message is unique. It is literally all ones in the host portion of the address. It acts as a megaphone.
Okay, so Unicast is a phone call, broadcast is a megaphone. What's the third?
Finally, there is multicast, which is one-to-many, but specifically targeted at a subscribed group.
Okay. Sort of like sending out an email newsletter. Not everyone in the company gets it, only the people who explicitly signed up for that mailing list.
A perfect comparison. For instance, the source mentions that routers use a mapping system called OSPF to automatically find the best paths through a network.
Right.
When OSPF routers talk to each other to share map updates, they use a specific multicast address, 224.200.200.55.
So only the routers actively running that mapping protocol will even bother opening the packet.
Precisely. Every other device in the network sees that address and immediately ignores it, which saves an immense amount of processing power.
That makes total sense.
And if we connect this to the bigger picture, understanding how devices talk locally brings up a massive global problem.
Right, because if devices rely on broadcasts and multicasts to function, what happens when millions of private networks try to connect to the global internet?
Chaos. We mentioned earlier that the world was running out of IPv4 addresses. In the mid-1990s, engineers realized a fundamental truth.
That we didn't have enough addresses for everyone.
Right. Not every single printer, laptop, and corporate server needed a globally unique public IP address that could be routed across the open internet.
There simply weren't enough unique 32-bit addresses in existence to give one to every single smart device on Earth. So the engineers walled off certain addresses specifically for private indoor use.
They did.
Yeah.
Defined in a famous document called RFC 1918.
RFC 1918, okay.
These are the addresses you probably see on your home Wi-Fi things, starting with 192.168 or a 10.net network.
Yeah, I see 192.168 all the time when I log into my router.
Exactly. You can use it internally as much as you want. But because millions of other households and corporations are using those exact same numbers inside their own walls, those private addresses are strictly forbidden from crossing the open internet. Routers will immediately drop them.
Which poses an obvious question. If my laptop is using a private IP address that is forbidden on the internet, how am I able to load a public website?
Through a process called Network Address Translation, or NAT. Think of your router as a corporate mailroom.
Okay, a mailroom.
When your laptop wants to request a web page, it sends a packet with its private internal address to the router. The router pauses the packet, strips off your private address, and essentially slaps its own globally unique public internet address on the return label.
Oh, I see. And it just keeps track of that swap.
Right. It records this swap in a massive internal ledger, noting your device's specific port number, and sends the packet out to the web server.
So the web server thinks it's just talking directly to my router. It sends the web page data back to the router's public address.
Yep.
Then the router checks its ledger, sees that my specific laptop initiated that request, changes the label back to my private IP, and hands it through the internal network to me.
And it does this for potentially thousands of packets a second, seamlessly.
That's incredible.
It is. Though the Swaler presentation does make a point to note that the IETF, the body that sets Internet standards, does not consider NAT to be a standalone security measure.
Oh, really? People always say NAT is a firewall.
It's a common misconception. It is a translation tool to save address space, not a dedicated firewall.
That is a vital distinction to make. And while we're on the topic of special addresses, the source brings up a few other interesting ones. It mentions a machine will use an APP address, which starts with 159.254 if its DHCP server fails.
Yes. APOB.
Since DHCP is the network's automatic IP distributor, what does the device do when it can't reach it?
Well, if a Windows machine boots up and asks the network for an IP address, and the distributor is offline, the machine doesn't just give up.
It has a backup plan.
Exactly. It auto-assigns itself one of those 169.254 addresses so that it can at least attempt to talk to other devices on its local link that might be in the same situation.
That's smart. And there's also the loopback address, right?
Right.
127.0.0.1.
Right. A device uses that to send a message entirely to itself, never letting the packet touch the physical network cable. It's a way for a machine to test if its own internal networking software stack is functioning properly.
The ultimate is this microphone on test.
Precisely. And this highly categorized modern system replaced a very old 1981 standard called classful addressing, where the early Internet pioneers handed out IP addresses in massive rigid blocks.
The presentation notes that Class A networks accounted for 50% of all IPv4 addresses, giving over 16 million addresses to single organizations.
It was a massive oversight.
Yeah, they wasted millions of them because an organization might only have 1,000 computers, but they were hoarding 16 million addresses.
Which is exactly why they had to invent classless addressing, private IPs, and NAT to stop the bleeding.
All right, so all these devices are sitting on these internal private networks using their private IPs, and they rely heavily on those broadcast megaphone messages we discussed earlier to find services and talk to each other locally.
They do.
But causality tells us that if every device relies on shouting to operate, what happens when a company grows and too many devices are shouting in the same room at once?
You experience what is called a broadcast flood, and it is an absolute network killer.
The source has a brilliant analogy for this. It says, a large broadcast domain is like getting an email address to your entire massive company when the content of the email really only applies to a few people in one department.
The dreaded reply all problem.
Exactly. Every single device on the network has to stop its actual work, open the broadcast packet, process the request, realize it doesn't apply to them, and then discard it.
It creates immense latency. And network switches the devices that physically connect laptops and printers together in an office. They're designed to flood broadcasts out of every single port.
Wait, really?
Yeah. A switch does not stop a broadcast. It amplifies the noise.
Let me make sure I'm visualizing this correctly. Since switches just flood broadcasts everywhere, but routers naturally block them, is the act of subnetting essentially just taking a router and building soundproof walls inside a giant, noisy warehouse?
That is a highly accurate way to frame it, actually. If you have a massive local area network with 400 users, every single broadcast message hits all 400 machines.
Which sounds awful.
It is. But if you introduce a router and mathematically chop that network into two separate subnets of 200 users each, you've built a soundproof wall.
So a broadcast sent in subnet A will hit the router interface and just die.
Exactly. It will not leak over and bother subnet B.
Meaning the overall performance of both networks drastically improves because machines aren't processing useless noise.
Performance improves, and crucial security boundaries are established. With that router in the middle, you can now implement access control lists.
Like saying, subnet A is strictly forbidden from initiating contact with subnet B.
Exactly. The source outlines 3 primary ways network admins design these boundaries.
Let's hear them.
First is by location, so perhaps configuring one subnet per physical floor of a building. Second, by function, so human resources gets one subnet and the engineering department gets a completely isolated one.
And the third,
by device type.
Such as putting all the networked printers and scanners on their own isolated subnet, keeping their constant status broadcast completely segregated from the actual user web traffic.
You got it.
So segmentation seems to be the hallmark of a healthy network. But if we know we must build these soundproof walls to stop the floods, how do we actually calculate where to place them?
It fundamentally comes down to the concept of borrowing bits. You look at your IP address, you take your host portion of the house numbers, and you steal some of those binary bits, flipping them to create more network bits.
You are turning house numbers into new street names.
Exactly. And there are 2 golden formulas you absolutely must memorize to do this.
Let's walk through them slowly because the math is where a lot of people just hit a wall.
Sure. Formula 1 dictates how many subnets you create. The formula is 2 to the power of n, where n represents the number of binary bits you just borrowed.
Wait, let me try this out loud to make sure the mechanics make sense. If I look at my host bits and I borrow just 2 of them, 2 to the power of 2 is 4.
Right.
So by borrowing 2 bits, I just built 4 soundproof rooms.
You did. You took one large network and sliced it into 4 separate subnets.
Okay, that covers how many rooms I built. What about figuring out how many devices I can actually put inside each of those new rooms?
That is Formula 2. It calculates the usable hosts per subnet. The formula is 2 to the power of h minus 2, where h is the number of host bits you still have left over after borrowing.
Let's shine a spotlight on that -2 rule, because it seems critical. If the binary math says a space can hold a certain number of addresses, why are we always subtracting 2 usable addresses from the final tally?
Because in every single subnet you ever create, the very first address and the very last address are permanently reserved by the system.
They can't be used for devices.
Right. They can never be assigned to a laptop or a server. The very first address, where all the remaining host bits are zeros, is the network address. It serves as the mathematical identity of the subnet itself.
Okay, and the last address?
The very last address, where all the remaining host bits are ones, is the broadcast address. That is the targeted megaphone we discussed earlier, used to shout to everyone on that specific subnet.
So if your host formula calculates that you have a block of 32 addresses, you only ever have 30 usable ones to assign to physical devices.
Correct. The source provides a fantastic real-world scale of how powerful this bit borrowing can be, actually.
Oh yeah, the ISP example.
Right. Imagine an internet service provider is handed a massive, private, 10^0 network with a /8 prefix. They decide to borrow 10 bits, changing that /8 into a /18 prefix.
So utilizing the first formula to find the number of subnets, 2 to the 10th power, that equates to 1,024 subnets.
Yes. They can instantly segment their massive block into 1,024 separate, isolated networks to hand out to different corporate clients.
That's huge.
But they started with 24 host bits and they borrowed 10. That leaves 14 host bits remaining for each of those new networks.
Okay, let me do the math on that one.
Go for it.
If we run the second formula 2 to the 14th power, -2, it reveals that every single one of those 1,024 subnets still contains over 16,000 usable host addresses.
Exactly. The sheer scale of the mathematics is staggering when you lay it out like that.
It really is. But as we move into the final concept from the source, there is a glaring flaw here if you rely strictly on this traditional method of subnetting.
No major flaw.
Because traditional subnetting assumes all of these blocks you are creating are the exact same size.
That is the big catch. And historically, it led to an enormous waste problem. Specifically concerning WAN links, the wide area network connections between routers.
The Solella presentation highlights this issue perfectly. Let's imagine you borrow bits and create a bunch of subnets using a /27 mask. Based on the math, a /27 gives you 30 usable hosts per subnet.
Right, 30 usable hosts.
If you have a branch office with 25 employees, handing them a subnet with 30 usable addresses is incredibly efficient.
Very clean.
But networks aren't just offices. They are connected by point-to-point router links, and a dedicated WAN cable connecting router A in New York to router B in London acts as its own tiny, isolated network.
A network that will only ever contain exactly 2 devices, router A and router B.
But if you are using traditional fixed-length subnetting across your organization, you are forced to assign one of your whole /27 blocks to that tiny WAN link.
Which is a disaster.
You are taking a network designed to hold 30 devices and assigning it to a cable that only requires 2. You are burning 28 perfectly good IP addresses into the ether every single time you connect 2 routers together.
It is deeply inefficient, especially when we consider how scarce IPv4 addresses became.
It's like forcing a pizzeria to cut every single pizza they bake into exactly 30 equal slices, regardless of the customer.
That's a great analogy.
Thanks. I mean, it works perfectly if you are feeding a massive party, but if you serve that same 30-slice pizza to just 2 people on a date, the rest goes straight into the trash. There had to be a way for engineers to cut custom slices.
And what's fascinating here is that the engineering community recognized this architectural flaw, and they developed a rather elegant solution called Variable Length Subnet Masking, commonly referred to as VLSM.
Variable length, implying the slices no longer have to remain uniform in size.
Exactly. VLSM is, conceptually, the act of subnetting a subnet.
Subnetting a subnet, okay.
You take one of those /27 blocks that contains 30 usable addresses, But instead of blindly assigning it to a router WAN link and wasting 28 addresses, you isolate that specific block and you run the math again. You borrow more bits just from that one individual slice.
Hold on, I'm losing you here. If I take a network and I've already mathematically sliced it into 30 uniform pieces, how does the router keep track if I take one of those slices and shred it into even smaller pieces? Doesn't the binary math overlap? How does a router know which slice is which?
It does not overlap because routers route data based on the most specific prefix length. If you chop a /27 down further into a /30, the router sees the /30 as a more specific set of instructions.
Oh, I see.
The math cleanly subdivides the space.
Mm.
A /30 prefix leaves exactly 2 host bits. 2 to the power of 2 is 4. Subtract the network address, subtract the broadcast address.
And you are left with exactly 2 usable host addresses.
Exactly.
Which is the exact perfect mathematical fit for a point-to-point router WAN link. 0 wasted addresses.
0 waste. You allocate your big /27 blocks to your local area networks that have lots of human users, and you utilize the custom-carved tiny /30 blocks exclusively for your router infrastructure.
It's brilliant.
It is, but executing this correctly requires extreme discipline, which brings us to a critical organizational principle.
The source outlines a very strict methodology for this, right? You can't just start carving slices randomly.
You absolutely cannot. The golden rule of VLSM is this: always size the largest subnet first.
The largest first. Okay.
When you are planning a network architecture, you must compile all of your requirements and sort them sequentially from largest to smallest. You carve out the massive chunks of contiguous addresses for your biggest departments first, and you systematically work your way down the list, ending with the tiny 2-address WAN links at the very bottom.
Because if you attempt to do it in reverse, if you start sprinkling tiny /30 WAN links at the very beginning of your binary address block,
you will fatally fragment your address space. You will box yourself into a mathematical corner and suddenly realize you do not have a continuous, unbroken block of binary bits left large enough to accommodate your 200-user engineering department.
Oh, wow.
Yeah, the bit boundaries must remain clean, which is why working biggest to smallest is a non-negotiable rule.
So what does this all mean for you, the listener, navigating the digital world right now? We have traversed a tremendous amount of invisible architecture today. We started by exploring the basic 32-bit anatomy of an IP address, decoded at the microchip level by the logical AND operation of the subnet mask.
We covered a lot of ground.
We really did. We looked at how network address translation acts as a global mailroom to save public IPs. We explored how engineers solved the latency of reply-all broadcast floods by building soundproof router walls. We unpacked the 2 golden mathematical formulas to calculate those walls.
And finally, we solved the pizzeria waste problem by utilizing the custom variable length sizing of VLSM.
It is a profound amount of logical architecture operating invisibly, flawlessly, all around us every second of the day. Next time you sit down at a coffee shop or log on to a corporate guest Wi-Fi network, just remember, this exact subnetting math is actively working right in that moment to keep your smartphone's web traffic segmented safely away from the company's internal servers.
It isn't magic happening behind that Wi-Fi icon. It is just brilliant, mathematically rigorous engineering.
Beautifully said.
But, I'd like to leave you with one final thought to ponder based on the historical context we discussed.
Absolutely. Go for it.
We noted that private RFC 1918 addresses, NAT, and this incredibly complex VLSM subnetting were all developed in the mid-1990s as basically desperate conservation methods.
Because the world was running out of standard IPv4 addresses.
Exactly. Now, the SOELA presentation explicitly states that a newer standard, IPv6, is the ultimate long-term solution to this address exhaustion. So, consider this. If the current IPv4 internet requires all of this incredibly complex mathematical slicing, dicing, bit borrowing, and active mailroom translation just to barely survive, what kind of mind-bending, almost infinite scale must the new IPv6 protocol possess to make every single one of these address conservation tricks completely obsolete?
Now that is an incredible sense of scale to think about the next time you connect your laptop to the world. Thanks for joining us on this deep dive. Keep asking questions, keep exploring the invisible architecture around you, and we will catch you next time.